Okay, we've talked about how to propagate wave fields, how to measure wave fields with holography and phase retrieval. So now we're ready to talk about, again, kind of the core problem of most computational imaging systems, how to estimate multidimensional objects, in this case a three-dimensional object. In chapter 4 we talked about projection tomography, where we inverted rays to reconstruct three-dimensional objects. Today we want to understand how to estimate three-dimensional objects when we measure the wave field. This is a paper that we talked about when we introduced tomography from Michael Feld's group at MIT on diffraction tomography of blood cells. The upper images are standard microscope images focused at some range, and the lower cells the lower images E through G and I through K are slices of three-dimensional tomographs. And what you see is that on the tomographs you don't really see the background blur that you see when you focus an image on a particular slice, because now you've computed the three-dimensional image from a variety of measured fields under various illumination conditions, and you have a true three-dimensional representation. Here the brightness represents refractive index at 633 nanometers, so the estimate done here is using the Ritov approximation, which is particularly useful for estimation of phase in objects, so you can get a three-dimensional image of the refractive index inside the material. The scale bar is at 10 microns, so these are roughly 10 micron cross cells and resolved to a submicron kind of accuracy. Optical coherence tomography is another example of diffraction tomography. In the case of OCT, it's a one-dimensional ranging tomography through a confocal system. This is an example of an eye reconstructed in 3 dimensions by scanned OCT, on the left using 1064 nanometer illumination, and on the right 800 and some nanometer illumination. This system uses a swept source, meaning that the wavelength of the illumination is changing in order to assist with acquisition of three-dimensional data. So we'll talk both about angular diffraction tomography and swept source multi-wavelength diffraction tomography today. Computational imaging. Episode 30, diffraction tomography. So earlier we talked about projection tomography, where we basically measure shadows of the object. We look at how rays or attenuators they propagate through the object and use the projection slice theorem to reconstruct the object from those projections. Today we're going to talk about diffraction tomography. So the object is illuminated with a coherent wave, and we measure the scatter of that wave, and then we need to analyze that scatter under various illumination conditions to try to reconstruct the three-dimensional object. To understand this problem, we need to consider wave propagation inside of the material. So this is the wave equation for the electric field and the wave equation for the magnetic field inside the material. We'll assume here that the magnetic moment is constant in the material, but the permittivity of the material varies, and so this is the electrical susceptibility, and this chi of R, that susceptibility, is the amplitude and phase of the scatter that we're going to try to reconstruct locally, the basic structure of the object. We can turn this differential wave equation into an integral form, as shown here with the Green's function. So the Green's function is the local wave field that's generated at each point, the impulse response for the scattering. Now we have an equation in the field itself, psi, that we can use to try to understand what is the scattered field. Of course, the problem here is that we can't evaluate this integral because we don't know what psi is. So this problem is often addressed using the Born approximation. So this is basically the integral form of the wave equation. We can take psi as generated from this integral form and substitute it into the equation to get an expansion. So we've replaced psi here with its integral form. Now we have psi naught scattered by the Green's function plus a second order term of the wave field itself scattered by the Green's function. Under the Born approximation, we assume that the scattered field is a permutation is a permutation of the illumination field, so that these higher order terms are small, and so then we can use the illumination field and generate the scattered field from the illumination field as the scatter. So now we have a relationship between the illumination field and the scattered field that we would measure, with modulated by the susceptibility of the material, which is the unknown that we're trying to find, the three-dimensional structure of the material. So now the question is, how do we invert this to find the wave field? We can look at the Fourier transform of this three-dimensional scattered field and find that it has this form, so that the Fourier transform of the scattered field is linearly proportional to a shifted version of the three-dimensional Fourier transform of the susceptibility with this pole due to the Green's function. So if we illuminated with a plane wave, let's say we have a plane wave U naught, the scattered field is the three-dimensional structure of the susceptibility on this sphere. This is the sphere corresponding to that pole in the scatter. So the magnitude of U, the wave vector for the scatter, is 1 over lambda as a requirement for the scattered field. So the scattered field sees the susceptibility on this sphere. The diameter of the radius of the sphere is 1 over lambda, because that's the magnitude of U for the scattered field, and its diameter is 2 over lambda. If we change the illumination direction, then we measure a different sphere, and so if we illuminate from a variety of different angles, we can fill out the Fourier space of the object and then inverse Fourier transform to recover the original object. If we think of this in terms of, like, we take the two-dimensional Fourier transform with respect to xy of the scattered field measured in a plane, that two-dimensional transform has this form. So basically what we're seeing then is the two-dimensional Fourier transform of the scatter along the Fourier transform directions integrated with respect to z. So with the projection tomography, with X-ray projections, we saw that the Fourier transform with respect to the distance from the origin was a slice of the Fourier transform of the object. Here we're seeing the same thing. We're seeing a projection of the Fourier transform of the object for each illumination direction, and we can fill that in to recover the original object. Typically, in diffraction tomography systems, we measure over some limited range of illumination angles and illumination frequencies. So if you illuminate with a single vector, let's say U naught here, and you measure over some angular range, what you'd measure be some slice of this Fourier transform. So that's what's shown here. A single view measures a manifold, a curved part of that sphere for that illumination direction. Now if we rotate, then we've rotated where that manifold is. So this is showing rotating the illumination direction over 15 degrees. And each time we rotate, we see a slice of the Fourier transform of the object. Now there's a missing cone here that because it rotates around a particular direction, we see the Fourier transform in this kind of butterfly shape. On the right, what's shown in here is the transmission direction. If instead of rotating, we change the illumination wavelength, what changing the illumination wavelength would do would be to change the radius of this sphere. So we're measuring, let's say, a slice here of this sphere. If we change the wavelength, then we just change that radius of the sphere, and we see this very small set of slices. We can look at these systems in a variety of different geometries. What's shown here on the left is slices of the object where we change the angle of illumination in the forward scattering geometry, and then on the right is slices of the Fourier transform of the object if we change the illumination direction at a single wavelength in a reflection geometry. This one on the far right here is in the reflection geometry. We're changing the radius of the sphere by changing the wavelength, but instead of looking at the forward scatter, we're looking at the back scatter. So the change in the illumination direction is linearly proportional to the change of the Fourier region that we see. In this case of changing the illumination frequency, that's basically equivalent to what we saw with the swept source OCT. Reconstruction is simply taking the Fourier transform of that block. So here's an example of the Shepp-Logan phantom. This is our original image. This is the Fourier transform. It's mostly a constant object, so the Fourier transform is 0 and centered around the origin. here is data that we would get if we changed the wavelength looking at this object. So we see this kind of Fourier transform structure of the object over a limited illumination direction just by changing the wavelength. And the horizontal axis here is different wavelengths, what the scatter looks like. We take the Fourier transform of that block of data and we recover a blurred version of the original object, with the blur due to the finite envelope that we're seeing in the Fourier space. So basically, that's how diffraction tomography works. We take a set of data, we fill in part of the Fourier space, we take the inverse transform over the part of the Fourier space that we've sampled, and we get a filtered version of the object due to the finite region of the Fourier space that we've sampled. And this can be done in a variety of geometries under a variety of illumination conditions. So this is a way to take the measured field and estimate the three-dimensional object. And that's kind of the core problem that we have in tomography, is that we want to not estimate the field that we've measured. We don't want to say the field is not the object. We want to estimate the object itself. We can do better than what we do with this sort of linear processing if we use a neural estimator. And so next time we're going to talk about strategies for taking limited sampling of the Fourier space of the object and turning that into an estimated object using a neural estimator.